Let's look at an example of using the limit definition of a function to find the derivative of the function 1 over x, and then find the value of that derivative at the point 0.52. So let's go ahead and get started by finding the derivative. So f prime of x is going to equal the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So everywhere there is an x in my function for this first part of my numerator, I will replace that x with an x plus delta x. So we get the limit as delta x goes to 0 of 1 over x plus delta x minus 1 over x all over delta x. Now, we cannot evaluate this a limit as it currently stands because as delta x goes to 0, my denominator goes to 0, which is undefined. So we're going to use some algebra to combine our two rational functions in our numerator, and in that process look for an opportunity to remove this delta x from our denominator. So we will have the limit as delta x goes to 0. To combine my two pieces in my numerator, I need a common denominator. That common denominator is going to end up being the product of my two denominators because they have no common factors. So we're going to get something like this. 1 over x plus delta x times x over x. That will create a denominator that is x times x plus delta x minus 1 over x times x plus delta x over x plus delta x. Again, creating this common denominator of x times delta x. Now that whole thing is my numerator, and my denominator is still delta x. Continuing on, the limit as delta x goes to 0. In my numerator, I have a common denominator now. That common denominator is x plus delta x times x. The numerator from this first term is simply x minus, and then the numerator from this second term is x plus delta x. Now notice it is minus or subtract that entire quantity. So we need to be careful with that minus sign, which is why I put parentheses around the x plus delta x. Now let's not forget that this all was the numerator, and we still have delta x as the denominator of our limit. So now we have the limit as delta x goes to 0. My denominator is delta x. And let's see what happens in our numerator. So I notice I have an x minus an x, so those will go to 0. And notice I have this negative that needs to be applied to the delta x. So we will have negative delta x in our numerator over at the quantity x plus delta x times x. And all of that is in our denominator. Now, to simplify things, what we're going to do is we're going to take this delta x that's in our denominator and we'll multiply by its reciprocal. And that will help us kind of clean things up for this limit. So we have the limit as delta x approaches 0. We have negative delta x over x plus delta x times x. And then, so that's my numerator. Now we're going to multiply by the reciprocal of the denominator. That's 1 over delta x. And now notice that we've set up a situation where the delta x in the numerator can divide out the delta x in the denominator. And so our issue with being able to find the limit as delta x goes to 0 is now resolved. And so we're really looking at what is the limit as delta x goes to 0 of negative 1, don't forget that negative out here in front, negative 1 over x plus delta x times x. Now, as delta x goes to 0, that numerator, negative 1, does not change. As delta x goes to 0, in my denominator, x plus delta x will go towards x plus 0, and x will just head towards x. So we end up with negative 1 over x squared. So our derivative, our f prime of x, is negative 1 over x squared. Now, we were asked to find the value of the derivative of the function at the point 1/2, 2. So notice that the input for the derivative function is an x value. So to find the value of the derivative of the function, I need to focus on the x value of the point we're interested in. So we would get f prime at 0.5 is equal to negative 1 over 0.5 squared. And if I square 0.5 or 1/2, I get 1/4. And so negative 1 divided by 1/4 is negative 4. So now let's use what we found out about the derivative of the function f of x equals 1 over x at the point 1/2, 2 to write the equation of the tangent line to the function at that point. So recall that the slope of the tangent line at 0.52 will equal f prime at 0.5 or at 1/2, and we found that to be negative 4 before. Also, we need to know that the tangent line is y equal the slope of the tangent line at 0.5 times x minus our known x value, so 0.5, plus our known y value, which is 2. In general, we could say that the tangent line is y equals the slope of the tangent line, which is f prime at x naught, at your known x value, times x minus x naught plus y naught. So that's a general formula that is useful and you should know. So now, to find our tangent line, we need y equals, we found that our derivative at 1/2 was -4 times x minus our known x value, so 1/2, plus our known y value. Now that's a perfectly good answer. If I so desired, I could write it in slope-intercept form. So I could simplify that using some algebra. So if I distribute the -4, I would get -4x plus, then 4 times 1/2 is 2, and that will be a +2 plus 2. So we would get y equals -4x plus 4 is another perfectly good way, perfectly acceptable way to express the equation of the tangent line. I hope this helps.